This week I'm going to start with a 20 or 30-minute recap of the ideas from last week's lesson, and then we will spend 50 or 60 minutes talking about fundamental matrices and repeated eigenvalues. After fundamental matrices, I will offer you the chance for a 10-minute break, and you can vote if you want one or not. In last week's lesson, I would have started talking about systems of differential equations, things like this. Suppose we have n variables and n equations, n linear differential equations. Now, this is a complicated way to write this. We can write this in a neater way if we use matrices. If we let x be the vector x1, x2 up to xn, by x prime, I mean the vector x1 prime, x2 prime, etc., etc. Capital P will be our square matrix, p11, p12, etc. And G will be our function g1, g2 up to gn. If we use these matrices, then the linear system at the top, that's n first-order linear differential equations in n variables, we could write that just as x prime is equal to p, x plus g. And that's, of course, a much neater and easier way to write this system. I want to extend some of the ideas from chapter 3 to systems. In chapter 3, we had multiple solutions to a second or higher order differential equation, and we were writing as y1 of t, y2t, etc. But we can't use the same notation here because we're already using x subscript 1, x subscript 2, etc. to denote coordinates or different variables. So we need a new type of notation for the different solutions to an equation. And what we're going to do is we're going to use superscript bracket. So x superscript bracket 1 or x superscript bracket 2. These are just going to be the different solutions. This doesn't mean x squared or two derivatives of x or anything like that. This just means solution number 2. Another idea from chapter 3, remember that if we have two solutions to our linear differential equation, any linear combination of y1 and y2 is also a solution. We have the same idea for linear systems. If x1 and x2 are two solutions to the linear homogeneous system x prime is equal to px, then every linear combination of x1 and x2 is also a solution. We can go further. We can say if x1, x2 up to xn are linearly independent solutions to this linear system, and here P is going to be an n by n matrix. So the same number, n solutions, n by n matrix. Then the theorem says every solution to the system can be written as a linear combination of these functions. And we can do it in exactly one way. So just the same thing that we were doing back in chapter 3. If we have this, then x1 up to xn, we say form a fundamental set of solutions, and we say that a linear combination of the functions in the fundamental set of solutions is the general solution to the linear system. Okay, but how do we find these solutions? Let's suppose we're looking at x prime is equal to ax, where A is an n by n matrix of numbers. It's an n by n matrix, and every entry in the matrix is a real number. The idea is this. Step 1, we need to find the eigenvalues of the matrix. Step 2, we want to find the eigenvectors of the matrix. And then the solution is going to be eigenvector e to the power eigenvalue t. The eigenvalues we're going to call R. Let's say Rj. The eigenvectors we're going to use xi. So let's write xij, and this is a vector, so let me underline it with a pen. And then the solution is eigenvector xi multiplied by the number e to the power eigenvalue t. So for example, solve x prime is equal to 1, 1, 4, 1, x. Step 1, find the eigenvalues. I'm just going to tell you that the eigenvalues of this matrix are 3 and minus 1. Step 2, find the eigenvectors. And I'm just going to tell you that the eigenvectors of this matrix could be 1, 2, and 1, minus 2. As soon as we know the eigenvalues and the eigenvectors, we can write down two solutions. It's always eigenvector e to the power eigenvalue t. The eigenvector is 1, 2. The eigenvalue is 3, so it's 1, 2 multiplied by e to the power 3t. And then we do the same for the second solution. It's always eigenvector e to the power eigenvalue t. The eigenvalue is minus 1, so it's going to be e to the power minus t, and the eigenvector is 1, minus 2. As soon as we have our two solutions, the general solution is going to be a linear combination of these two functions. So the general solution to this system is C1, 1, 2, e to the power 3t, plus C2, 1 minus 2, e to the power minus t. Let's do another example. Solve x prime is equal to 8 minus 1, 6, 1, x, with the initial condition x at time t is 0 is equal to 1 minus 2. To solve this initial value problem, first we're going to find the eigenvalues and the eigenvectors of the matrix, and we'll use that to write down the general solution. And then to finish, we'll use the initial condition to find the constants C1 and C2. I'm trusting that you know how to find eigenvalues and eigenvectors, so I'm just going to tell you that the eigenvalues are 7 and 2, and the eigenvectors are 1, 1 and 1, 6. I leave this for you to check. As soon as we know these, we can write down the general solution. Constant eigenvector e to the power eigenvalue t plus constant eigenvector e to the power eigenvalue t. To finish this problem, we need to find C1 and C2. So we take our formula, take our general solution I've written at the top, and we put t equal to 0, and we want this to be equal to 1 minus 2. If t is 0, we just get C1, 1, 1 plus C2, 1, 6, or C1 plus C2, C1 plus 6 C2. That gives us a linear system of two equations in two unknowns. You know how to solve that from your linear algebra course. So I'll tell you that the answers are 8 over 5 and minus 3 over 5. And then we can write down the solution to the initial value problem. 8 over 5, eigenvector e to the power eigenvalue t, minus 3 over 5, eigenvector e to the power eigenvalue t. Okay, that's the easiest case, but there's actually 3 cases we should be thinking about. There's 3 possibilities for the eigenvalues of a square matrix A. Either all the eigenvalues are real and different, or some of the eigenvalues occur in complex conjugate pairs, or some of the eigenvalues are repeated. The two examples I've shown you so far are both from case 1. That's the easiest case. If all the eigenvalues are real and different, then we know from linear algebra that that means all of the eigenvectors are linearly independent. If the eigenvectors are linearly independent, then that means, using the way that we're writing down x1, x2, etc. before, that means that the Wronskian of these is going to be non-zero, because the Wronskian of linearly independent eigenvectors is not 0. And if the Wronskian is not 0, then x1 up to xn must be linearly independent functions. So they form a fundamental set of solutions. It's possible that we could have repeated eigenvalues but still have n linearly independent eigenvectors. If that's true, then this is also true. The Wronskian is non-zero. We have linearly independent solutions, so we have a fundamental set of solutions, and there's nothing else to do. I'll show you an example of this case. Solve x prime is equal to 0, 1, 1, 1, 0, 1, 1, 1, 0, x. And I'm going to tell you that the eigenvalues and the eigenvectors are these. Now, note that we have repeated eigenvalues here. R2 is -1 and R3 is also -1. But we have 3 linearly independent eigenvectors. And if we have 3 linearly independent eigenvectors, then that means we have 3 linearly independent solutions. How do we know they're linearly independent? We calculate the Wronskian of them. I'm going to leave that for you to do. You can check that the Wronskian of these 3 functions is non-zero. That means that these 3 functions form a fundamental set of solutions. And if we have a fundamental set of solutions, then straight away we can write down the general solution to the linear system. So if we have repeated eigenvalues, but we still have n linearly independent eigenvectors, then there's no problem. We'll just do what we were doing before. Eigenvector e to the power eigenvalue t. We'll end up with a fundamental set of solutions. We'll end up being able to write down our general solution. Sometimes, though, we don't have that. Sometimes if we have repeated eigenvalues, we do not have enough eigenvectors. We're going to study that later today. There was one more case, and that was complex eigenvalues. Let's go back to talking about x prime is equal to ax, where A is an n by n matrix of real numbers. Writing r to the power n cross n is a way of writing the set of all n by n matrices of real numbers. So we're thinking about things like x1 prime, x2 prime up to xn prime is equal to this square matrix multiplied by x1, x2 up to xn. And of course, let me just remind you, what that really means is this linear system. x1 prime is a11 x1 plus a12 x2 plus ... plus a1n xn, etc. Really, we have n first order homogeneous linear differential equations or with n different variables. Let's talk about complex eigenvalues now. What do we do if we have complex eigenvalues of this square matrix? Well, we know from linear algebra that any complex eigenvalues must occur in complex conjugate pairs. In other words, if lambda plus I mu is an eigenvalue, where lambda and mu are real numbers, then the complex conjugate of this, that's lambda minus I mu, must also be an eigenvalue of A. We also know from linear algebra that if xi1 is an eigenvector of A, then the complex conjugate of xi1 is also an eigenvector of A. So we could write down two solutions. Just as we were doing before, eigenvector e to the power eigenvalue t. But the problem here, these are not real valued functions. These functions map from the real numbers. In other words, the t that we put into the function is a real number, but we're given a complex vector. And we don't want that. We want functions which map from the real numbers to Rn. We want to get out a real valued vector. So we're going to have to adapt some of the ideas from chapter 3. First of all, some notation. Let's suppose our eigenvalue is lambda plus I mu, and let's suppose our eigenvector is A plus IB. Here, lambda and mu are going to be real numbers. A and B are going to be real valued vectors. Then our solution x1 is A plus IB, e to the power lambda plus I mu t. Think back to chapter 3. We know how to do e to the power of a complex number. What that really means is e to the power lambda t cos mu t plus I sine mu t. Now I want to multiply this out and then gather the real terms together and gather the imaginary terms together. How do we get a real term? We can do A multiplied by cos, or we could do IB multiplied by I sine, because I squared is minus 1. We get minus B sine. How can we get a complex term? I could do A multiplied by I sine, or I could do IB multiplied by cos. Now these terms which I've colored are the functions that we're going to be using. The green terms I'm going to call the function u, and this orange terms I'm going to call the function v. What we've done is we've taken our solution x1 and we've written this as real function plus I real function. Why are we doing this? Because the functions u and v are going to be will solve the differential equation. Functions u and v are going to be linearly independent, and the span of u and v is going to be the same as the span of x1 and x2. So what does that mean? That means that instead of using x1 and x2, we could use u and v in our fundamental set of solutions. Okay, let's do an example. How do we solve something like this? X prime is equal to minus a half 1 minus 1 minus a half x. First, we need the eigenvalues and the eigenvectors. I will show you the calculation. The eigenvalues are minus a half plus I and minus a half minus I. We don't need both of these because we're going to get our functions u and v in a different way. We only need to use one of these. And it doesn't matter which one we use. I'm going to choose R1. That means we do not need R2. We need an eigenvector. So the usual way, we can find that the eigenvector corresponding to R1 is 1i. Now note that as soon as we know xi1, we immediately know xi2, because xi2 is just a complex conjugate of xi1. But we're not using R2, so we're not using xi2. So just forget about this. We don't need this. What we want is R1 and we want xi1. Next, we want to look at x1, the solution that we get using the first eigenvalue and the first eigenvector. That's eigenvector e to the power eigenvalue t, or 1i e to the power minus t over 2 cos t plus I sine t. And I want to rearrange this to write this as real valued vector function plus I real valued vector function. So just playing with it, I can write this as e to the power minus t over 2 cos t minus sine t, that's the real terms, plus I e to the power minus t over 2 sine t cos t. That's the imaginary terms. I'm just rearranging it so that all the terms involving I are at the end and all the terms which don't have an I are near the start. And these are the functions that we want. This is going to be our u and our v. So u is going to be e to the power minus t over 2 cos t minus sine t, and v is going to be e to the power minus t over 2 sine t cos t. As soon as we know u and v, we can write down the general solution to the linear system. It's just going to be constant u plus constant v, or c1 e to the power minus t over 2 cos t minus sine t, plus c2 e to the power minus t over 2 sine t cos t. So that's what we do if we have complex eigenvalues. Let me just recap that. Our method to solve a linear system is this. Step 1, find the eigenvalues. Step 2, find the eigenvectors. Step 3, if Rj is real, then we just use the solution eigenvector e to the power eigenvalue t. And as long as we have enough linearly independent eigenvectors, that's enough. But if our eigenvalue is a complex number, then we need to play with this formula. We need to rearrange it so that we have real valued function plus I real valued functions. And then we use this green function and we use this orange function in our general solution instead of using x1 and x2. Okay, that's a very quick recap of what would have been last week's lesson. If you look at the lecture notes, or if you watch the recording of the lecture covering these sections, you'll see there's lots more details and there's lots more examples in the lecture notes or in the recording of the lecture. Please read those or watch those, and please ask me on the discussion board or during this lesson if you have any questions, if anything is unclear. Today's lesson starts now. The first of two topics that I want to talk about today is the idea of fundamental matrices. In this section, we're going to be looking at the linear system x prime is equal to ptx, where now pt is going to be an n by n matrix function. It's an n by n matrix where each entry in the matrix is a function. And I want to suppose that we have n linearly independent solutions to this differential equation, to this linear system. In other words, I want to suppose that x1 up to xn form a fundamental set of solutions to this ODE. Then we can write them in a matrix like this. I'm going to write a square matrix where the first column of the matrix is the first solution. And then the second column of the matrix is the second solution, and so on. And I'm going to call this matrix capital Psi. If I have a matrix where the columns of the matrix are the functions in the fundamental set of solutions, then this matrix is called a fundamental matrix. So, for example, find a fundamental matrix for the linear system x prime is equal to 1, 1, 4, 1, x. I've already talked about this today, so let me just remind you. We already have a fundamental set of solutions of this equation. All we're going to do is we're going to write down the matrix where we use this green function and this orange function to give us the columns of the matrix. Here we are. The first column, e to the power 3t, so that's 1 multiplied by e to the power 3t. And then the second column is going to be 2 multiplied by e to the power 3t. Second entry in the first column, 2e to the 3t. And then we do the same thing for the right-hand column. 1 e to the power minus t minus 2 e to the power minus t. And that is it. We just take our fundamental set of solutions and we use them as the columns of the fundamental matrix. Why are we doing this? The general solution can be written as a linear combination of the functions in the fundamental set of solutions. But that's just the same as writing fundamental matrix multiplied by C, where C is just a constant vector. We could always write the general solution of our linear system as just fundamental matrix multiplied by C. And if we had an initial condition, x at time t0 is the vector x0, put this into the equation, put this into xt is equal to fundamental matrix C. We get fundamental matrix at time t0, C is equal to x0. Okay, and put these at the top. There's the general solution on the left, and top right we have the information from our initial condition. But remember, if we have a fundamental set of solutions, then these functions are linearly independent. If they're linearly independent, then the fundamental matrix must be an invertible matrix. If xi is invertible, then the top right equation is just the same as C is equal to psi inverse at time t0, x0. And what we can do is we can take this and just put it into our general solution. That means that the solution to the initial value problem, x prime is equal to ax with the initial condition x at time 0 is x0, we can just write as x of t is equal to psi t, psi inverse at t0, x0. Okay, we'll come back to that later. We'll be using that particularly next week. Suppose that psi is a fundamental matrix for x prime is equal to ptx. Then this fundamental matrix solves the same differential equation. It solves xi prime is equal to pt xi. And I'm going to leave this for you to prove. This is one of the exercises in the lecture notes. You should be able to prove this. But basically, because every column of the fundamental matrix is a solution of the differential equation, you use that information to show that the whole matrix solves basically the same differential equation. This is something important we're going to use later, so remember that. Remember that xi prime is always equal to pt xi. Instead, I want to move to a different idea now. We've just been talking about a fundamental matrix, but there's actually a special fundamental matrix. And there's a special fundamental matrix which has the property that capital phi at time t0, that's the time we use for the initial condition in the initial value problem, is equal to the identity matrix. Now, in terms of notation, whenever we're talking about this special fundamental matrix, which has this special property that phi at time t0 is the identity matrix, we're going to use the letter capital phi. If we're just talking about any fundamental matrix, and of which there are infinitely many for any linear system, we're going to use the notation capital psi. Okay, consider x prime is equal to 1, 1, 4, 1, x. Find the special fundamental matrix which satisfies phi of 0 is equal to the identity matrix. Okay, so we need to find a matrix where each of the columns of the matrix is a solution to the differential equation. And we want the first column, when we set time t to be equal to 0, to be 1, 0. So in other words, to get the first column, we need to solve the differential equation with the initial condition x of 0 is 1, 0. The second column of our special fundamental matrix is also going to be a solution to the differential equation. But this time, we want our solution to satisfy the initial condition 0, 1, because we want to get 0, 1 in phi 0. To answer this problem, we need to solve two initial value problems. We've already looked at this differential equation, so I can tell you that we've already found that the general solution to this differential equation is constant 1, 2 e to the power 3t plus constant 1 minus 2 e to the power minus t. We need to choose the constant so that we can satisfy the two initial conditions. First, let's do the left column. We need x at time 0 to be 1, 0. We need to find the C1 and the C2 which satisfy this. And I'll leave it for you to check. We need C1 as a half and C2 is also a half. So our first function is going to be a half e to the power 3t plus a half e to the power minus t, e to the power 3t minus e to the power minus t. This is going to be the left column of our special fundamental matrix. And then we do the same thing for the right column, except this time we want the initial condition to be 0, 1. And so this time we find that the constants must be a quarter and minus a quarter. Now that we have these, we can write down the special fundamental matrix. The green function in the left column and the orange function becomes the right column. Next idea. What is e to the power of a matrix multiplied by t? Now, if instead of a matrix we just had a number here, e to the power number at, we know that's the solution to this initial value problem. The solution to x prime is equal to ax, where little a is just a number, x times 0 is x0, is just x0 e to the power 80. And we know from calculus that the Taylor series for this function, or some people use this as the definition of the exponential function, 1 plus the power series, starting n is equal to 1, of an t to the power n over n factorial. I want to use the same ideas for e to the power matrix capital AT. So instead of x prime is equal to a number ax, I want to look at x prime is equal to a matrix capital to ax with the initial condition x at 0 is x0. I want to define the exponential of capital AT to be the identity matrix plus the power series starting at n equal to 1, capital A to the power n, t to the power n over n factorial. That's just the same that I had on the previous slide, except instead of the number 1, we have the identity first. And instead of the number, small a, we have the matrix, capital A. Now, does this work? Let's check this definition. I want to differentiate the exponential of the matrix capital AT. In other words, I want to differentiate I plus the power series ANTN over n factorial. And don't worry about radii of convergence or anything like that. Just for this course, just imagine this is well defined, it converges, don't worry about that. As long as it converges, absolutely, we're allowed to take the derivative inside the power series. Derivative I, that's a constant matrix, of course, just the zero matrix. Derivative of the power series is just power series derivative of ANTN over n factorial. We know how to differentiate t to the power n. Of course, it's just n t to the power n minus 1. N cancels with one of the n's on the bottom, and we end up with an t to the power n minus 1 over n minus 1 factorial. The first one, where n is equal to 1, is going to be a to the power 1, t to the power 0 divided by 0 factorial. In other words, the first term is just going to be a, and then we would have this formula which starts at n equal to 2. Let's do a substitution because I don't want a series which starts at 2, I want a series which starts at 1. So I'm going to do the substitution. K is equal to n minus 1. So then it's a plus the series, a to the power k plus 1, t to the power k divided by k factorial. Take a factor of a out, and it's a multiplied by open bracket, identity matrix plus the power series starting at k equal to 1, a to the power k, t to the power k over k factorial. And what's this? What's this in the bracket? This is exactly what we started with. We just have capital A multiplied by the exponential of AT. Because the derivative of the exponential of AT is A exponential of AT, that means exponential of AT solves this initial condition. It solves the differential equation, it solves the initial condition at time t equal to 0 is equal to the identity matrix. But wait a minute, the special fundamental matrix capital Phi solves the same initial value problem. Derivative of capital Phi is A capital Phi. Capital Phi times 0 is equal to I. And there's always a unique solution to an initial value problem. So these two functions must be the same. The exponential function of AT is the same as the special fundamental matrix, which satisfies capital Phi at 0 is equal to the identity matrix. So for example, let's suppose that capital A is 8 minus 1, 6, 1, and you're asked to find the exponential of AT. Remember, so really we're being asked to find the special fundamental matrix, which satisfies phi of 0 is I. So there's another way of writing the question, find the special fundamental matrix. We've previously looked at x prime is equal to ax for this matrix A, and we found that the general solution is constant 1, 1 e to the power 70 plus constant 1, 6 e to the power 2, 2. So to answer this question, we need to solve two initial variables. We need to choose the constants, which makes x at time 0, 1, 0, and we need to choose the correct constants, which makes x at time 0 equal to 0, 1. First, to satisfy the initial condition x at 0 is equal to 1, 0, we need the constant 6 over 5 and minus 1 over 5. I leave that for you to check. So our first function, that means the first column of our matrix, is this function I've written in green. And then we do the same thing, but with the initial condition 0, 1 instead. And then we find, I leave this for you to check, that the constants we want are minus 1 over 5 and 1 over 5. So we get this orange function. This is going to be the second column of our answer. As soon as we know these two functions, the green function and the orange function, we can write down the answer. The answer is the exponential of capital AT. That's the same as the special fundamental matrix capital Phi, is the 2 by 2 matrix where the first column is this green function and the second column is the orange function. The next topic is the idea of diagonalizable matrices. Again, some things you've studied in linear algebra. Why are we interested in here? Because if we have a diagonal matrix, then it's easy to calculate the exponential of capital DT, because we just have the diagonal matrix where the entries on the main diagonal are e to the power r1t, e to the power r2t, e to the power r3t, etc. And that's going to make our life much easier if we have a diagonal matrix. Now consider x prime is equal to ax for an n by n matrix of real numbers. I'm going to remind you of how we diagonalize capital A. if we have eigenvectors of A, and if these are linearly independent, we could write a matrix capital T, where the first column is the first eigenvector, second column is the second eigenvector, and so on. As long as this determinant of this matrix is not 0, in other words, as long as these eigenvectors are linearly independent, then T inverse exists. If T inverse exists, then T inverse AT is a diagonal matrix. In other words, matrix capital A is diagonalizable. All of this should be familiar to you from your linear algebra course. For example, diagonalize the matrix 1, 1, 4, 1. We need the eigenvalues and the eigenvectors. Here they are. We take our eigenvectors and we use them to write the matrix capital T. T is 1, 1, 2, minus 2. First column, first eigenvector, second column, second eigenvector. We need the inverse of capital T. You know how to do this. And then we calculate T inverse AT. And we always get a diagonal matrix where the entries on the main diagonal are the eigenvalues. In this case, 3 and minus 1. Okay, let's go back to the general case. Now consider x prime is equal to ax. What I want to do is I want to define a new variable y like this. X is equal to ty, or y is equal to t inverse x. And let me just slow down here. This is the key step here for this method. Anytime we're going to use this method to solve a linear system, we're always defining a new variable y using x is equal to ty. Let me explain why we're doing this. If we're doing this, then x prime is equal to ax is the same as saying ty prime is equal to aty. Multiply on the left by t inverse. That's the same as y prime is equal to t inverse aty, but that's just the same as a diagonal matrix dy. Why are we doing this? Because it's easy to find a fundamental matrix for y prime is equal to dy. A fundamental matrix is just exponential of capital DT. As soon as we know the eigenvalues, R1, R2, up to Rn, we can write that down straight away. But remember, x was equal to ty. If we know a fundamental matrix for the y equation, then we can just multiply it on the left by t, and we get a fundamental matrix for the differential equation that we started with. And that's the key idea here. We diagonalize our matrix in order to change our possibly difficult differential equation into an easy one. We find the fundamental matrix, and then we multiply it on the left by t to go back to the variable that we want. Find a fundamental matrix for x prime is equal to 1, 1, 4, 1, x. We're going to diagonalize this using capital T and end up with the easier system, the easier equation, y prime is equal to 3, 0, 0, minus 1, x. It's easy to find the fundamental matrix for this equation. It's just e to the power 3t, 0, 0, e to the power minus 1. It's just the exponential of dt, or e to the power dt. And then as soon as we know this, We just multiplied on the left by t, like this, and we end up with a fundamental matrix for the equation that we started with. This is a method we're going to be using next week when we look at non-homogeneous linear systems. So please revise these ideas before we do next week when we start looking at more difficult equations. I have one more topic for today, and that's the topic of repeated eigenvalues, but it's more precise than that. Is repeated eigenvalues when we don't have n linearly independent eigenvectors. Before I start that, would you like a 10-minute break? And let's continue. Our second topic for today's lesson is the idea of repeated eigenvalues when we don't have n linearly independent eigenvectors. For example, find the eigenvalues and the eigenvectors of the matrix 1, -1, 1, 3. Using our eigenvalue equation, we can calculate that 0 must be the determinant of A minus Ri. That's the determinant of 1 minus R, -1, 1, 3 minus R. R squared minus 4R plus 4, but that's just R minus 2 squared. So we have a repeated eigenvalue of 2. And then we can calculate the eigenvectors using our eigenvector equation. 0 vector is A minus Ri vector, xi. We find that we could choose xi is 1 minus 1. There's only one linearly independent eigenvector here. So how do we solve x prime is equal to 1 minus 1, 1, 3x if we only have one linearly independent eigenvector? We know that eigenvector e to the power eigenvalue t, or 1 minus 1 e to the power 2t, is a solution, but that's not enough. We need two solutions. Let's make a guess. We use the same ideas that we used back in chapter 3 when we needed another solution. We could try multiplying it by t. So if our second solution is eigenvector t e to the power eigenvalue t, we can try putting this into the differential equation. The derivative of this is going to be xi e to the power 2t plus 2 xi t e to the power 2t. And a multiplied by this function is a xi t e to the power 2t. There's e to the power 2t terms all the way through, and these are not always non-zero, so we can cancel these out. And then rearrange it a little bit. That's the same as wanting xi plus 2 xi minus a xi t is equal to the 0 vector. And we want that to be true for all t. In particular, we want it to be true when time t is 0. But if t is 0, then all of this is 0, and we would just have xi is equal to 0. 0 is not an eigenvector. This guess did not work. Let's try again. Same first part as before. Some vector xi, t e to the power 2t, but now I want to try adding on an extra term, plus another vector. This time I'm using the Greek letter eta, multiplied by e to the power 2t. Let's try again. Let's start with the differential equation that we want to be true, and then put this function into it. The derivative of this function is going to be xi e to the power 2t plus 2 xi t e to the power 2t plus 2 eta e to the power 2t. And we want this to be equal to a multiplied by x2. We want this to be equal to a xi t e to the power 2t plus eta e to the power 2t. Now, as before, I'm going to cancel out all of the e to the power 2t terms. And then I'm going to simplify, rearrange this a little bit. That's the same as 2 xi minus a xi t plus xi plus 2 eta minus a eta is equal to 0. And this needs to be true for all time t. For example, if we say this must be true for time t equal to 0, then the first term is just 0. We would need to have xi plus 2 eta minus a eta is equal to 0. And if the second term is equal to 0, forget about that for the moment, if this is all at 0. And if we say we want this to be true at time t equal to 1, but then we would just end up with 2 xi minus a xi is equal to 0. We need we need xi and eta to satisfy these two equations. The first one looks familiar. The first one is just the equation for an eigenvector. So we need to have that xi is the eigenvector. Clearly, xi is 1 minus 1. Then we want to use the second equation to calculate an eta. So we want minus 1 minus 1, 1, 1, eta 1, eta 2 to be equal to the eigenvector 1 minus 1. From this, we see that we must have that eta 1 plus eta 2 is equal to minus 1. So general eta must be some number k and then minus 1 minus k. Or we can split this up into two. A vector 0 minus 1 plus k multiplied by 1 minus 1 for some k. And then after we know that, we can put that into our formula, and we can find that our second solution would be 1 minus 1t, e to the power 2t, plus 0 minus 1, e to the power 2t, plus k, 1 minus 1, e to the power 2t. But the last term here is just a number, k, multiplied by the first solution. And we're trying to find a linearly independent second solution. We don't need something which includes a multiple of our first solution. Because we already have x1, it's okay to choose k equal to 0. So our second solution is going to be eigenvector t, e to the power eigenvalue t, plus this new extra vector, which in this example is 0 minus 1, e to the power 2t. And after we know this, after we know our second solution, we can write down that the general solution of the differential equation is a linear combination of x1 and x2. I'll come back and I'll summarize this method later. First, find a fundamental matrix for x prime is equal to 1 minus 1, 1, 3x. Then, in part 2 of the question, find a special fundamental matrix, capital phi, which satisfies phi at 0 is equal to I. Well, we know our two solutions. We know our fundamental set of solutions. We'll use these as the columns in our fundamental matrix. First function gives us the first column, e to the power 2t minus e to the power 2t. And the second function gives us our second column, t e to the power 2t minus t e to the power 2t minus e to the power 2t. This is a fundamental matrix for this system. Rewrite this at the top. Now, we also want to find the special fundamental matrix which satisfies capital phi of 0 is the identity. That's the same as the exponential of at. Now, if we take the fundamental matrix we've just found, and if we set t equal to 0, we get the matrix 1, 0, minus 1, minus 1. And if we then take the inverse of this matrix, we get 1, 0, minus 1, minus 1. Why am I doing this? Because the one that we want, the capital phi that we want to find, is the same as this fundamental matrix capital Xi multiplied by xi inverse at time 0. So to finish this question, we just need to multiply two matrices together. And when we multiply these together, we get the answer e to the power 2t, which I've taken outside, 1 minus t, t, 1 plus t. And just look at this. If t is equal to 0, what do we get? We get the identity matrix. Here's another formula to remember if you're asked for the special fundamental matrix. Okay, so let's just recap the ideas here. If we have two repeated eigenvalues, but we have only one linearly independent eigenvector, then there's two equations that we need to remember. The second solution is eigenvector xi, t e to the power rt, plus a new vector eta e to the power rt, where eta comes from the equation a minus ri eta is equal to xi. There's a name for the vector eta. Eta is called a generalized eigenvector of A. So here's our method. If we have two repeated eigenvalues, but only one linearly independent eigenvector, step 1, find the eigenvalues and the eigenvectors. Step 2, the first solution is just eigenvector e to the power eigenvalue t, just as we've been doing before. Step 3, we need to find a generalized eigenvector eta. That's a vector eta which satisfies the equation a minus ri eta is equal to xi. And then as soon as we know eta, we can write down that the second solution is eigenvalue t e to the power eigenvector xi t e to the power eigenvalue t plus generalized eigenvector e to the power eigenvalue t. Xi t e to the power rt plus eta e to the power rt. Okay, let's do an example. Solve x prime is equal to minus 5 over 2, 3 over 2, minus 3 over 2, 1 over 2 x with the initial condition 3 minus 1. Step 1 is to find the eigenvalues and the eigenvectors, and I'm just going to tell you the answer. For this matrix, there's only one eigenvalue, a repeated eigenvalue, which is minus 1. And there's only one linearly independent eigenvector. We could take 1, 1. So straight away, we could write down one solution of this linear system, 1, 1 e to the power minus t. We need to find a second linearly independent solution, and we're going to use as the solution of the form xi t e to the power minus t plus eta e to the power minus t, where xi is the eigenvector 1, 1 that we've just found, and eta is a generalized eigenvector. So what we do is we take the generalized eigenvector equation and we use that to find the vector eta. Okay, solving this equation, starting with a minus ri eta is equal to xi, which for this example is minus 3 over 2, 3 over 2, minus 3 over 2, 3 over 2, eta 1, eta 2 is equal to 1, 1. Or minus 3 over 2, eta 1 plus 3 over 2, eta 2 is equal to 1. Multiply everything by 2/3 to simplify a little bit. That's the same as minus eta 1 plus eta 2 is equal to 2/3. We need any vector which satisfies this equation. We don't need to have every one, we just need one of them. So choose one of these coordinates to be 0 to make it a little bit easier, and then use this equation to find the other one. I'm choosing that the first coordinate is 0. I'm choosing eta1 is 0. And then I can read off eta2 is 2/3. If you wanted to do, you could do it another way. You could choose eta2 is 0, or any number that you want, really, and then you could read off eta1. Now, let me just note, we don't need to find every generalized eigenvector. Last time I did this, when I was trying to explain the ideas, I tried to put a k in and to find every generalized eigenvector, but we don't need to do that because we already have our first solution. So it's okay to take k equal to 0. It's okay to just take any generalized eigenvector which satisfies the equation. We only need one generalized eigenvector, so we could use eta is equal to 0 2/3. Okay, now we know the eigenvalue, we know the eigenvector, we know the generalized eigenvector. As soon as we know these, we can write down our two solutions. The first solution is just eigenvector e to the power eigenvalue t. The second solution is eigenvector t e to the power eigenvalue t plus generalized eigenvector e to the power eigenvalue t. And then after we know these two solutions, we know how to continue. We can write down the general solution, constant green function plus constant orange function. And then we use the initial condition. I'm being deliberately quick at this point, to find the constants. And in this case, you can check that the constants need to be 3 and -6. And then we have everything that we need to write down the solution to the initial value problem. After simplifying a little bit, I like to see the answer of as the form 3 minus 1 e to the power minus t minus 6 1 1 t e to the power minus t. A quick check before we go on. What happens if we put t equal to 0? Well, all of this is 0. This is 1. We just end up with 3 minus 1. Yep, that's correct. So worth doing a quick check here. Another problem. Solve x prime is 1 minus 4, 4 minus 7x, with the initial condition x of 0 is 3, 2. Step 1, find the eigenvalues and the eigenvectors. And I'm just going to tell you here, there's only one eigenvalue. Here it's -3. And there's only one eigenvector, 1, 1. Now, previously when I was teaching this course, a student asked me, is it always 1, 1? And the answer is no. It's just a coincidence that the last example and this example, the eigenvector has been 1, 1. There's nothing special here. It just happens to be that the eigenvectors of these matrices are 1, 1. But you could get any vector here. As soon as we know the eigenvalue and the eigenvector, we know the first solution. 1, 1 e to the power 3t. What are we always doing? Eigenvector e to the power eigenvalue t. What do we do next? Next, we need to find a generalized eigenvector, eta. How do we do that? We do that using the equation a minus ri eta is equal to psi. One of the equations that you definitely have to remember for the final exam. So for this example, a minus ri is 4 minus 4, 4 minus 4. So we want 4 minus 4, 4 minus 4, e to 1, e to 2 is equal to 1, 1. We want 4e to 1 minus 4e to 2 is equal to 1, or dividing through by minus 4, we want minus e to 1 plus e to 2 is equal to minus a quarter. Rearrange it slightly. We want e to 2 is e to 1 minus a quarter. And we can choose any vector eta which satisfies this equation. There's infinitely many correct choices here, just any vector that satisfies this. Because I like easy vectors, I'm going to choose e to 1 to be 0 again, and then I could read off that e to 2 needs to be minus a quarter. So I'm going to choose the generalized eigenvector 0 minus a quarter. Okay, now we know the eigenvalue, we know the eigenvector, we know the generalized eigenvector. That's all we need to write down the second solution. Eigenvector t, e to the power eigenvalue t, plus generalized eigenvector e to the power eigenvalue t, or 1, 1t e to the power minus 3t plus 0 minus a quarter e to the minus 3t. And now that we know our two solutions, we can write down the general solution to the differential equation. What's left? All that's left is to find C1 and C2, which satisfies the initial conditions. Put it in t equal to 0. 3, 2 must be C1, 1, 1, plus C2, 0, minus a quarter. It helps that I chose one of these numbers to be 0 because it makes it easier to read off that C1 must be 3. And then after we know C1, we can find C2. So the solution to the initial value problem, 3 multiplied by the first function plus 4 multiplied by the second function. To finish, let's simplify this a little bit. Gather the e to the power minus 3t terms together, and we get 3, 2. That's 3 multiplied by 1, 1 just here, plus 4 multiplied by 0 minus a quarter gives 3, 2. Or we could write this in another way. We could write this as 3 plus 4t, 2 plus 4t, e to the power minus 3t. And either one of these last two lines is an acceptable answer. And then I come to the end of this week's lesson. That just leaves one topic to study, quite a difficult topic perhaps. Next week, we are going to study non-homogeneous linear systems. Are there any questions?